Hello everyone and thanks for watching Edupedia World videos. So continuing with chemical equilibrium, today we'll start a new topic called Chateliers Principle. Okay, so like I said before, this is a very important topic. Most of the time questions come from this topic of this chapter in your competitive examinations and even your school examinations. Okay, you can always find at least one question from Chateliers Principle directly. Okay, so mostly it is a qualitative concept. Okay, so it basically talks to you about what happens to a system at equilibrium as we change various factors like concentration, pressure, volume, temperature, etc. Alright, so basically Le Chatelier's principle is a principle which will help us to decide the effect of various factors on a reaction at equilibrium. Okay, so what is the statement of the principle? Okay, one of the statement is whenever a change is applied to a system at equilibrium. Okay, so first requisite over here is that your system is already present at equilibrium. Okay, so that means Q is equal to K equilibrium. Okay, that is the rate of forward reaction is equal to rate of backward reaction. Alright, and the system is at equilibrium. So whenever a change is applied to that system which is already present at equilibrium, the system tries to minimize the effect of that change. Okay, this can be one of the statements of your Le Chatelier's principle. Okay? It can be stated in different words. Okay, you will find it in different sentences, in different way, in different texts and literature, but this is the simplest one which we can come up with, that whenever a change is applied to any system present at equilibrium, that system itself, okay, this is done by the system itself. Okay, the change here was externally applied, the change was applied by me to the system. Okay, and now the system will counteract that change. Okay, the system by itself will try to minimize the effect of whatever change I applied over there. Alright, so this is being done by the system itself. So this principle, Le Chatelier's principle, is going to be applicable to both physical as well as chemical equilibrium. Okay, though we are basically focusing on chemical equilibria, towards the end of the chapter we'll look at some examples of physical equilibria as well. Okay, and do remember that Le Chatelier's principle is applicable over there as well. Okay, though it might be a bit difficult to apply in all of the cases of physical equilibrium except some. Alright, so we might not use it directly, but it is applicable technically speaking. Okay, so why is it so? Why is Le Chatelier principle, okay, saying that whenever I try to make some changes to the system at equilibrium, my system will automatically try to minimize the effect of that change. See, basically what happens is any system, okay, or any process in the world usually wants to achieve equilibrium. Okay, not even usually, it basically always wants to achieve a stable state. Okay, a state of minimum energy, a state of equilibrium. So it's like this. Say you have a U-shaped surface, okay, and you have a bearing ball over here. A ball bearing is present with you. Alright, and right now let's say this is the state of equilibrium of your ball here. Alright, so now if you shift or if you disturb this position of equilibrium, okay, that is if you take the ball on the right hand side or whether you take the ball on the left hand side and leave it over there, that is if you apply even a small change over here, the ball by itself, this whole system by itself will try to minimize the effect of that change. How is it so? Let's say if I push the ball towards right, okay, so then this is the new position of my bearing ball. Okay, this my ball bearing is present over here right now. So now this is not a stable state. Okay, so what will happen? As soon as I leave the ball over here, I have pushed it, okay, by this delta x amount and I have left it over here. Okay, it will automatically, okay, automatically go back to its initial position. Okay, it will automatically try to go in the backward direction and reach where it was initially present. Okay, so this is what happens with the system at equilibrium as well. Wherever I apply any small change, the system by itself will try to minimize the effect of that change. Okay, so even if I push the ball in the other direction on the left hand side, okay, once again the this system, okay, of this container and the ball will automatically, okay, try to change the position of ball once again, okay, to the equilibrium position. All right, it will automatically, as a result of gravity, okay, it will automatically push the ball towards the equilibrium position over here. So something of the same sort happens in case of physical and chemical equilibrium as well. Okay, the system by itself wants to stay in the state of equilibrium. So whenever we disturb that state, whenever we apply some change to that state, the system by itself will minimize the effect of that change as much as is possible for it to do so, right? So basically what happens is, at equilibrium we know Q is equal to K equilibrium. So if I apply any change to my system, okay, so for example, if I apply a change of concentration, pressure or volume, okay, etc, etc, the kinds of changes which we are talking about, I will show you on the next slide. Okay, so whenever those changes are applied, K equilibrium usually remains constant. Okay, but what changes is the Q value. Okay, because of the change, Q value changes. All right, whereas K equilibrium remains same. Okay, that is why the system will get disturbed. Okay, because Q is no more equal to K equilibrium, and hence it will once again try to change itself to make Q equals to K equilibrium. So if we analyze this same thing, this state of equilibrium and Chateliers principle in further detail, why it happens, okay, whatever happens. See, basically the main basic reason you can say is that K equilibrium, the equilibrium constant, is a function of temperature and temperature only. That is, for a given chemical reaction or a physical reaction, okay, and given stoichiometric coefficients. Alright, you cannot change stoichiometric coefficients once the reaction has been fixed. So for a given chemical or physical reaction of any physical process or chemical process, equilibrium constant for that process, okay, is function only of temperature, and it does not depend on any other values like concentrations, pressure, volume or whatever else you might think of. Okay, there is no way equilibrium constant can change unless you are changing the reaction itself or stoichiometry, or if you are changing the temperature. Okay, so because of this, K equilibrium remains constant. Alright, and since all the reactions are going to achieve or attain equilibrium eventually, okay, so this means that every reversible process has a tendency to go back to the position or state of equilibrium, and that is why whenever you change, you disturb the system already at equilibrium, the system will automatically minimize whatever change you had applied. Okay, it will automatically try to counteract that change. Okay, so that is what we are going to analyze over here, and that is why Chatelier principle said that system will minimize the effect of that change, because K equilibrium cannot change. Okay, K equilibrium remains constant, only Q value will get changed. Okay, at equilibrium Q was equal to K equilibrium, so now either Q will increase to a new value or it will decrease to another new value. Okay, so one of these things might take place. Alright, and whenever that happens, the system will make the reaction go in either forward direction or backward direction. Okay, and once again, make Q equals to K equilibrium. Alright, because if system has to counteract the change I have applied, how can it counteract that change? Okay, the only thing system can do is either it can go in forward direction or it can go in backward direction. There is nothing else which it can do. Alright, so that means to counteract the change I have applied, system will either, okay, it will either reinforce the forward reaction or it will reinforce the backward reaction. Okay, or it might reinforce both of them. Okay, or it might decide that my system, my state is not really disturbed and I don't have to do anything over here. Okay, so one by one we'll look at different cases and what happens when. Okay, so basically we are going to study over here effect of change in concentration of your reactants or products at equilibrium. Okay, then we will look at effect of pressure, effect of volume, okay, and effect of catalyst, inert gas addition. Alright, and at the end we'll look at effect of temperature. Okay, so this effect of temperature, though we'll look at it from the perspective of Chatelier principle as well, but here equilibrium constant changes. Okay, as we have studied that equilibrium constant is a function of temperature. So if I change temperature, the effect will be change in equilibrium constant itself. But in rest of the cases, equilibrium constant cannot change. Okay, even if I make changes in concentration, pressure, volume, catalyst, inert gas addition, this value will always remain constant. Okay, so let's start with the effect of change in concentration. So effect of concentration. Okay, basically, alright, here what we are talking about is moles per liter, that is molarity of your constituents present in your reaction process. Okay, so either I'm going to change concentration of my reactants, that is left hand side, or I'm going to change concentrations of my products, which is at right hand side. So let's look at both of them one by one. So what happens if I change the concentration of my reactants? So either I can increase their concentration or decrease their concentration. So if I increase the concentration, okay, of my reactants, my reaction shifts in forward direction. Okay, what do I mean by that? See, right now the system is at equilibrium. That means that rate of forward reaction is equal to the rate of backward reaction. Alright, so RF is equal to RB at this moment. Now if I change, okay, if I change the concentration and increase the concentration on the left hand side, okay, the reaction, okay, the reaction will shift the whole equilibrium towards forward direction. That is, it will increase the rate of forward reaction, okay, and make it more than the rate of backward reaction. Okay, it can do that. Alright, the reaction by itself can do that. So this is what will happen over here if I increase the concentration of my reactant. What happens if I decrease the concentration? The opposite thing happens. Okay, if I decrease the concentration on the left hand side, okay, that is, if I remove some of the content from over here, okay, if I remove and take them somewhere else. Alright, so here, as soon as I remove my reactants, okay, what will reaction do? Once again, the state of equilibrium has been disturbed, so it will either shift itself forward or backward. This time it shifts itself backward, that is, it increases the rate of backward reaction and makes it greater than forward rate of reaction. Okay, so this is what happens with increase or decrease of concentration of reactant. Okay, and similarly, you can also now guess what will happen if I change the concentration of products. Okay, so what happens is, if I increase the concentration of my products, okay, basically I am increasing the molarities on the right hand side. So as soon as I do that, what happens is reaction will shift the rate, okay, in the backward direction. That is, the reaction, the equilibrium gets shifted in the backward direction, or in other words, rate of backward reaction becomes greater than rate of forward reaction. Alright, and vice versa, if you decrease the, okay, inversely, if you decrease the rate concentration on the product side, it will shift the reaction in forward direction. That is, decrease in product will make RF greater than RB. Okay, whereas decrease in reactants used to make RF, okay, less than RB. That is, it shifts in backward direction. Here it shifts in forward direction. Okay, so you have to remember these things. What happens if I change the concentration of reactant, and what happens if I change the concentration of product? Okay, it is pretty simple. If you change, okay, if you change the concentration on any one side, okay, let's say if you increase the concentration on one side, okay, the reaction will shift in the opposite direction. And if you decrease the concentration on one side, the reaction shifts in the same direction. Alright, so this is how you can memorize it. Why does this happen? Okay, so the explanation is pretty simple. Alright, you can look at it from the perspective of the Le-Chatelier principle statement, okay, or you can also look at it from the perspective of the mathematical, okay, equation, that is Q equals to K equilibrium. Right, so let's look at it from Le-Chatelier's principle perspective. What did Le-Chatelier principle say? It says that whenever I apply some change, the system by itself will minimize the effect of that change. Okay, so let's take any particular reaction, okay, where we have reactants on the left hand side, say R1 and R2, and they are forming reversibly products P1 and P2. Okay, so now here, if I increase the concentration of my reactants, alright, so what is the change which I have applied? I have increased the concentration, I have increased the molarities over here on the left hand side. And what will system do? Whenever I make some change at equilibrium, the system will counteract that change. What will system do? it will try to decrease this increase in molarities. Okay, so since I have increased the molarity, system will work in a way such that it can again decrease these molarities. And how can it decrease the concentration of reactants? By shifting on the forward side. Okay, that is by forming more and more products. Alright, it will be able to consume more and more reactants if it increases the rate of forward reaction while keeping rate of backward reaction same or decreasing. Alright, so this is why reaction shifts in forward direction. Okay, or otherwise you can also say, what if I decrease the molarity? Okay, so now if I decrease the molarity of reactants, okay, that is I'm decreasing the concentration of reactants, system will again try to counteract this change applied by me. Okay, so I have disturbed the equilibrium, okay, in such a way that I have decreased the amount of reactants. So system will try to again increase the amount of reactants. Alright, and how can it increase the amount of reactants? By forming more and more reactants, that is by consuming more and more products and converting them into reactants, that is by shifting the reaction in the backward direction. Alright, so from Le-Chatelier's principle you can directly think why this happens. Alright, and mathematically speaking, why this occurs? Okay, basically say I have a reactant over here forming product. The stoichiometric coefficients are small r and small p. Okay, so right now my Q is equal to concentration of P raised to stoichiometric coefficient, concentration of R raised to stoichiometric coefficient. Alright, so this is equal to your K equilibrium, which is concentration of P at equilibrium, okay, raised to small p, divided by concentration of R at equilibrium raised to small r. Okay, so that is to say, right now the concentrations are concentrations at equilibrium, and that is why Q is equal to K equilibrium. So let's talk from the product's perspective. What happens if I increase the concentration of product now? K equilibrium cannot change. K equilibrium will only change if I change the reaction itself, that is by changing the stoichiometry or reactants in products, or if I change the temperature. Okay, so this value will remain same. What's going to change is this side. Okay, this side is going to get changed. Alright, so it might change in such a way that they are no more equal. So it might change in such a way that they are no more equal. What will I do then? I will try to make them equal again. Okay, so right now I have increased the concentration of product. So that means I have increased the numerator over here while keeping the denominator same. So that means Q has increased. So now Q is no more equal to K equilibrium. In fact, now Q is greater than K equilibrium. Okay, by increasing the concentration of products, I have made Q greater than K equilibrium. So if you remember the direction of reaction based on the Q value, whenever Q is greater than K equilibrium, the reaction shifts in forward direction. Okay, likewise, if I decrease the concentration of product, that is if I decrease the numerator, okay, that means I have decreased the value of Q. Okay, here if Q is less than K equilibrium, this means the reaction shifts in forward direction, and if Q is greater than K equilibrium, this means reaction shifts in backward direction. Okay, this is what is studied. Alright, so you can look at it from the perspective of Le-Chatelier's principle or from the perspective of Q value, that is reaction quotient. Let's look at it from the reactant side. Alright, the same thing. What if I change the concentration of reactant? Okay, so if I increase the concentration of my reactant at equilibrium, so right now Q is equal to K equilibrium, but as soon as I increase the concentration of reactant, it will once again become not equal to K equilibrium. Alright, so that means it will once again shift the reaction in such a way that Q is again equal to K equilibrium. So how will it change that? So if I increase the concentration of reactant, I am decreasing this whole ratio. That means I am decreasing Q value. So by increasing concentration of reactant, Q becomes less than K equilibrium. And whenever Q is less than K equilibrium, reaction is moving or going to shift in forward direction. That is, rate of forward reaction is going to be greater than rate of backward reaction. Right? Okay, on the other hand, if I decrease the concentration of reactant, that means I am increasing the Q value. Okay, so as soon as I increase the concentration of reactant, my state of equilibrium gets disturbed such that Q has now increased, and become greater than K equilibrium, because of which the reaction shifts in backward direction. That is, rate of backward reaction becomes greater than rate of forward reaction. Okay. Now here let's take an example and see one more important point over here. Okay. So before that, okay, before looking at it qualitatively, let's look at the same thing graphically. Okay, let's take an actual example and study this point. Okay, what happens graphically? Say I have a reaction N2 plus 3H2 reversibly forming twice of ammonia. So in this reaction, okay, I have reactants N2 and H2 and product ammonia. Let's assume initially I only started with nitrogen and hydrogen. Okay, so this is my initial nitrogen and this is my initial hydrogen concentration on the y-axis. Alright, and the progress of reaction, that is time, is shown on the x-axis. Okay, and amount of ammonia initially is assumed to be 0. So as the reaction proceeds, okay, the amount of ammonia increases and finally becomes constant. Okay, similarly amount of nitrogen decreases, okay, and then eventually becomes constant. All right, twice the amount of hydrogen also decreases and eventually becomes constant. Okay, so this is what happens in this reaction. Okay, amount of nitrogen hydrogen decreases, amount of ammonia increases, and finally after equilibrium is achieved, after T equilibrium, all of them are at a constant value. Okay, so let's say after this time they are all at constant values. So this whole thing over here, this is where equilibrium exists. Okay, now what if I disturb the equilibrium at this point? Okay, at this point T2 I disturb the equilibrium. Okay, let's say I am disturbing the equilibrium by suddenly increasing the concentration of my hydrogen present. Okay, right now they are all at constant values. Okay, concentration of hydrogen, concentration of nitrogen, concentration of ammonia, they are all at constant values. They are not going to change unless I externally change them. So let's say I have externally changed the concentration of hydrogen suddenly at time T2, that is I have suddenly put in more hydrogen in my container while keeping the amount of nitrogen and ammonia at the same values. What happens then? So the graph of hydrogen will suddenly see a jump. Okay, it was moving like this, but now it will suddenly increase and reach to this value. Okay, whereas the graphs of nitrogen will remain at the same position, the graph of ammonia will also remain at the same position. Okay, now what will happen? Since I have increased the concentration on reactant side, okay, the reaction will counteract this change and try to decrease the amount of reactants. That means it will shift the whole reaction in the forward direction. Okay, so what will happen is, once again the reaction will occur and this time it will occur in forward direction again. So amount of hydrogen will again decrease. Okay, and how much will it decrease? We cannot say. We'll actually have to make calculations to analyze that. Okay, but usually it will tend to be higher than the initial value. Okay, if the initial value was here, it will be somewhat higher than that initial values. Okay, this is how it will change. All right, so this is how it might look. Okay, but since the whole reaction is moving forward, right, so even the amount of nitrogen will decrease. Okay, because whenever reaction moves forward, the reactants get consumed. So though I did not change the concentration of nitrogen, it is bound to get somewhat decrease. Okay, and since the reaction has shifted in the forward direction, the amount of ammonia is going to increase. That means though I did not change the amount of ammonia here at equilibrium at T2, it will, okay, again start increasing before becoming constant. Okay, so this is how the graph changes, and this is where you can say the new equilibrium state is achieved. All right, and then once again your system continues to move at equilibrium. Okay, now what happens again after say time T3? All right, after T3 over here, I once again disturb my equilibrium. Okay, this is the new equilibrium established and I decide to disturb this new equilibrium. So once again the K equilibrium will remain constant but Q value will change, and let's say this time the disturbance is by increasing the concentration of ammonia. That is, right now my concentration of ammonia is over here, so I have suddenly increased it to, let's say, this value, while keeping the amount of hydrogen at the same position and the amount of nitrogen at the same position as they originally were. Okay, so this time, okay, since the amount of ammonia has been increased, that is, the amount of product has been increased, my reaction will shift in the backward direction. Okay, to counteract that change, that means this time amount of ammonia is going to decrease with time until equilibrium is achieved, and the amount of nitrogen and hydrogen is going to increase with time until equilibrium is achieved. That is to say, I am over here, so this time amount of ammonia, instead of increasing, will decrease by a bit and then become constant. Okay, alright, it will become constant once equilibrium is re-established. Okay, until then it will keep on decreasing. Okay, but since backward reaction is taking place, the amount of nitrogen will this time increase and then become constant. Okay, likewise amount of hydrogen will also somewhat increase and then become constant. Okay, so in this way. Okay, so this is how the graph will now look if I suddenly increase the concentration of ammonia at equilibrium. Okay, and say this will be the new time when equilibrium is once more established. Alright, so this is how changes take place. You can take any example, okay, any random reaction. You can even take physical reactions, okay, physical processes, that is where phase is changing, okay, rather than chemical reactions. Even then the graph will look in a similar fashion, right? So last important point over here, let's look at it via an example. Okay, say I have this reaction where solid carbon is reacting with gaseous carbon dioxide to form gaseous carbon monoxide. Alright, this is a system. Let's assume that right now it is at equilibrium. Okay, so what will happen if I change the concentrations now? Okay, it's pretty simple. If I increase the concentration of carbon monoxide, my reaction will shift in backward direction. Whereas if I increase the concentration of carbon dioxide, it will shift in forward direction. But what about carbon? Okay, what happens if I change the concentration of carbon? Well, carbon is a pure solid. So pure solid and pure liquids, okay, if you change their concentrations at equilibrium, the system remains unaffected. That is, the state of equilibrium is not disturbed by changing the concentrations of pure solid and pure liquid. Okay, you can understand this mathematically. See, basically Q is equal to K equilibrium. Okay, at equilibrium this is true, alright, and this means concentration of CO, okay, divided by concentration of CO2 is equal to concentration of CO at equilibrium divided by concentration of CO2 at equilibrium. That is, right now the concentrations are concentrations at equilibrium. Now let's assume I suddenly increase the concentration of carbon over here. Okay, so do you see any change in the value of, okay, the value of Q is determined only by CO and CO2. Okay, there is no expression of carbon in this entire expression over anywhere. Okay, in this equation there is no carbon, because we know that pure solid and pure liquids do not feature in the expressions of reaction coefficient or equilibrium constant. Only aqueous substances, that is substances in solutions, or gaseous substances come in the expressions. So that is to say that even if I increase or if I decrease the amount of carbon present with me at equilibrium, okay, the Q value is not disturbed, K value is not disturbed, that is your equilibrium state is not disturbed. Okay, the state of equilibrium remains undisturbed, that is unaffected, and hence the reaction will not have to counteract any change, because there is no effective change as far as the reaction is concerned, and hence the reaction will neither shift in forward direction nor in backward direction. It will continue to move on at the same rates in both the direction. Okay, and the concentrations will also remain the same, that is concentration of rest of the constituents except carbon, which I have increased or decreased externally. Alright, so this is all you need to know about effect of changes in concentration on the systems present at equilibrium. Okay, so you should remember this, what happens if I change the concentration of reactant, what happens if I change the concentration of product, why heat happens, okay, why is also very important. And you should also remember what happens to the graph, how do they change if I change concentrations. And lastly, you should remember that pure solids and pure liquids do not affect the equilibrium state. Okay, in the next session we will look at the effect of pressure, alright, and go through the same criteria, same analysis for the pressure what we did today for the concentration. Okay, so until next time, and once again thanks for watching Edupedia World video.